The universe is vast and ancient. It's filled with stars, planets, and galaxies. But have you ever wondered how it all began? What was there before the universe existed? The truth is, we don't know for sure. Our current understanding of physics breaks down when we try to go back to the very beginning. Imagine a time before time, a place before space. It's hard to wrap our minds around. Some theories suggest that the universe was once incredibly small and dense, perhaps even infinitely so. This state is often described as a singularity, a point where our current laws of physics no longer apply. Others propose the existence of a multiverse, an infinite expanse containing countless universes, each with its own unique properties. In this scenario, our universe might be just one of many bubbles that have popped into existence. The nature of the pre-Big Bang universe remains one of the greatest mysteries in cosmology. However, we do have a compelling theory that explains what happened next, the Big Bang. About 13.8 billion years ago, something incredible happened. The universe, once incredibly small and hot, began to expand rapidly. This expansion, known as the Big Bang, marked the beginning of space and time as we know them. Imagine a tiny speck, smaller than an atom, containing all the energy and matter that would become our universe. Suddenly, this speck began to expand. It wasn't an explosion in the traditional sense, with matter flying outward into pre-existing space. Instead, space itself was expanding, carrying everything along with it. This expansion was incredibly rapid, much faster than the speed of light. In a tiny fraction of a second, the universe grew from an infinitesimally small point to an enormous size. This period, known as inflation, is a crucial part of the Big Bang theory. As the universe expanded, it also cooled down. Imagine a hot oven cooling as it's turned off. Similarly, the intense heat of the early universe began to dissipate. This cooling allowed for the formation of the first particles. Initially, the universe was a swirling soup of elementary particles like quarks, leptons, and bosons. These particles interacted with each other at incredibly high energies. As the universe cooled, these particles began to combine, forming protons and neutrons, the building blocks of atoms. This period, known as baryogenesis, is still not fully understood. It's a key area of research in cosmology, as it helps explain why the universe is made up of matter and not antimatter. As the universe continued to cool, protons and neutrons began to combine through nuclear fusion, forming the first atomic nuclei. This process, known as Big Bang nucleosynthesis, lasted for about 3 minutes. During this time, the universe was like a giant nuclear reactor, forging the light elements that would become the building blocks of stars and galaxies. The primary elements created during this period were hydrogen, helium, and trace amounts of lithium and beryllium. These elements, the simplest and lightest in the periodic table, would later play a crucial role in the formation of stars and galaxies, seeding the universe with the raw materials for future generations of stars and planets. The formation of these elements marked a significant step in the evolution of the universe. It transitioned from a hot, dense soup of elementary particles to a cooler, more structured environment where the building blocks of matter had emerged. Section 5. Cosmic Background Radiation, an Echo of the Big Bang. One of the most compelling pieces of evidence supporting the Big Bang theory is the cosmic microwave background radiation, or CMB. This faint afterglow of the Big Bang permeates the universe and provides a glimpse into the early universe just 380,000 years after the Big Bang. Imagine the universe as a hot, glowing ball of plasma. As the universe expanded and cooled, this plasma eventually cooled enough for electrons to combine with atomic nuclei, forming neutral atoms. This event, known as recombination, allowed light to travel freely through the universe for the first time. This light, initially very energetic, has been stretched over billions of years by the expansion of the universe, shifting it into the microwave part of the electromagnetic spectrum. This faint afterglow, known as the cosmic microwave background radiation, provides a snapshot of the universe when it was just a baby, a mere 380,000 years old. Section 6. Formation of galaxies and stars, gravity at work. Over millions of years, gravity began to play a crucial role in shaping the universe. The tiny density fluctuations present in the early universe, amplified by gravity, caused matter to clump together. These clumps grew larger over time, attracting more and more matter. Imagine a snowball rolling down a hill, gathering more snow as it goes. Similarly, these clumps of matter, drawn together by gravity, eventually became dense enough to ignite nuclear fusion in their cores, giving birth to the first stars. These early stars, much larger and hotter than our Sun, lived short but brilliant lives, forging heavier elements in their cores through nuclear fusion. When these stars exploded as supernovae, they scattered these heavier elements into space, enriching the surrounding gas clouds. Section 7. Our solar system, a tiny part of a vast universe. About 4.6 billion years ago, in a relatively quiet corner of the Milky Way galaxy, a vast cloud of gas and dust began to collapse under its own gravity. This cloud, enriched by the remnants of previous generations of stars, contained all the elements necessary for the formation of our solar system. As the cloud collapsed, it began to spin faster and faster, forming a rotating disk of material. At the center of this disk, gravity pulled most of the material inward, forming the Sun. The remaining material, swirling around the newborn Sun, clumped together to form the planets, moons, asteroids, and comets of our solar system. Our solar system, a cosmic oasis teeming with life, is just one of billions of planetary systems in the Milky Way galaxy, itself just one of billions of galaxies in the observable universe. Section 8. Continuing expansion, the universe today. The universe continues to expand and evolve today, driven by a mysterious force known as dark energy. This expansion, once thought to be slowing down due to gravity, is now accelerating, pushing galaxies farther apart at an ever-increasing rate. Imagine baking a loaf of raisin bread. As the bread bakes and expands, the raisins within it move farther apart. Similarly, the expansion of the universe is carrying galaxies away from each other like raisins in an expanding loaf of bread. The discovery of dark energy revolutionized our understanding of the universe, raising profound questions about its ultimate fate. Will the universe continue to expand forever, growing colder and darker as galaxies drift apart? Or will gravity eventually halt and reverse the expansion, leading to a big crunch? Section 9. Unveiling the mysteries, the future of cosmology. The Big Bang Theory provides a compelling framework for understanding the origin and evolution of the universe, but many mysteries remain. What is dark energy, and what is its role in the universe? What happened before the Big Bang? Are there other universes out there? Cosmology, the study of the universe as a whole, is a vibrant and rapidly evolving field. Scientists are constantly developing new theories and conducting experiments to test our understanding of the universe. New telescopes and space missions are providing unprecedented views of the cosmos, allowing us to peer deeper into space and time than ever before. The quest to understand the universe is a journey of discovery, pushing the boundaries of human knowledge and imagination. As we continue to explore the cosmos, we can expect even more surprising discoveries, challenging our current understanding of the universe and revealing the secrets of its origin and evolution.